Now we're going to talk about how the value of Kc changes when you modify reaction equations. So an equilibrium constant describes some chemistry, right? And it is always true, and that equilibrium is always the same, right? The actual balance of the reactants, the products, the ions, the solid, the acids, the bases, whatever it is, that equilibrium constant describes that balance. The Kc comes from our chemical equation. Chemical equation is a representation that we come up with for the chemistry. We choose the reactants, we choose the products, we choose what sort of particular chemistry we want to focus in on. The underlying chemistry doesn't change though. But if we change the representation, the value of Kc will change in a predictable way based on how we're changing that representation. But importantly, the underlying chemistry does not change. So chemistry is going to always be balanced. Whatever molecules are stable, whatever molecules are present the most at equilibrium, will always still be reflected in that sort of description or whatever the equilibrium constant is based on how you're representing it. Is the common thing or the dominant species a reactant or is it a product? Kc will change to reflect. So the most common way, or kind of the most intuitive way we can change a reaction is we can reverse the direction that we see it in. So for example, H2 plus I2 gives you 2HI. The equilibrium constant for that is 3.9. So that is reflecting, slight product favored equilibrium. Kc is greater than 1. If you think about the reverse reaction, HI, 2HI becoming H2 plus I2, it's the exact same conversion between basically HI and the elements. In order to understand the equilibrium constant for this reverse reaction, you just do 1 divided by the equilibrium constant of the top reaction. So you just invert it and you get, say, 0.25. And all that's going on is you're just swapping what you call the reactants and what you call the products, right? The volume of the equilibrium constant just reflects that, right? This shows slight product favored. This shows slight reactant favored, right? These aren't 10 to the 10th, 10 to the negative 10th, anything like that. It's like 4 forward, about a quarter backwards. So let's look at an example to kind of see what's going on here. So let's look at this reaction. We can either think about it as H2 plus I2 becoming HI, or starting with HI. So we could start with all what we'll call the reactants, or we could start with all products. This would be our initial reaction mixture. So this is not at equilibrium, and we're going to let both of these react and reach an equilibrium. And those equilibriums need to look the same because it's the same chemistry, right? You can go through and count. It's 4 HI molecules, 2 I2s, and 2 H2s, right? The underlying chemistry is exactly the same. The dominant molecule is HI and HI. The Kc value changes, just basically reflecting, are you calling HI a product or are you calling it a reactant, right? How are you kind of considering or constructing your view or description of the reaction? But the chemistry is always the same. The equilibrium always has to look the same because it's the same chemical, same molecules reacting in the same way. We can also look at a bit more extreme of reaction, the combustion of propane, C3H8 plus 5O2 gives me 3O2 and 4H2O. So the Kc for that is 10 to the 40th. If we reverse the reaction, again, we just invert the equilibrium constant. So the reverse reaction is the Kc of 10 to the negative 40th. So we can see we go from a very product favored, a reaction that goes to completion. The reverse would be very, very reactant favored and does not happen. Right? These two things would be the opposite. The reason why this top reaction goes to completion is that the reverse direction does not happen. So when you make this CO2 and this H2O, it doesn't change back, right? It just stays as the product. As we can see, this reverse reaction is the one that does not happen. And importantly, in both of these descriptions, the same compounds are always on the favored side of the reaction, the CO2 and the H2O. That's what's favored in the chemistry. Whatever side you choose to put it on, the value of Kc will change to reflect that preference.
Second way that we can change a reaction is to modify the coefficients, to multiply all the coefficients out. So this is not something that we oftentimes do in the case of just like thinking about interpreting chemistry, but we'll see it come up here as a very practical application, especially in terms of like mechanisms that we've seen before, combining reactions together. So you can multiply all of your coefficients by a constant factor. So we'll look at the same reaction. H2, 1H2, 1I2 gives me 2HI. We could multiply all those coefficients by 2. Still be the same ratio, 2 to 4 is the same description. So what you do in that case is you take your coefficients, you can see they've all been squared if we think about actually constructing the equilibrium constant. They've all just been doubled, and so 2 to 4. And what that functionally does is you've squared the equilibrium constant. So the value is squared as well. So your 3.9 was the equilibrium constant for, we'll say, the simple reaction. The larger coefficients reaction has an equilibrium constant of 15. It just kind of becomes bigger, and it kind of just reflects the fact that there's just like more molecules reacting. It's just you've changed how you're describing the reaction, kind of bigger stakes, more molecules reacting, more molecules being produced. So the equilibrium constant changes again to reflect that.
The other thing that we can do is we can add reactions together. So this is something that we've seen previously, for example, in like looking at mechanisms, the idea of two reactions that can kind of go in sequence to cause some sort of overall reaction. Well, each individual reaction would be in equilibrium. And what we want to do is we want to combine them and be able to predict basically what the equilibrium constant would be for the overall reaction. So we can see this process. These are generic formulas that we saw previously, like A plus B gives you C, and then that C reacts with more B to give you D. So this like C is like a reaction intermediate or something like that. It gets turned into, reacts with more B, the B compound, and then turns into the D product. And so the overall process is a little bit of A with a lot of B gives you the overall D product. And the equilibrium constant for the sum of the sum reaction is going to be the product of the equilibrium constants of the component reactions. So you multiply basically the equilibrium constants of your component of the, say, step 1, step 2, and those would combine to give you the equilibrium constant of the sum. This is just showing the work. Trust me, it works. Basically what happens is the C terms cancel out, and then the B's combine to give you that square, and that just is consistent with what we see for delineating how we've defined equilibrium constants up there. So if you're combining an equilibrium, two reactions to equal an overall reaction, you're adding those together. That's the same thing as multiplying the equilibrium constants together. So let's look at this kind of an example where we're given, how we would kind of use this is we would be given, say, information on reference equilibrium constants. Say xenon plus fluorine gives you xenon difluorine, Kc is 124. Xenon plus 2 fluorines give you xenon tetrafluoride, and Kc is 782. So those are kind of reference reactions that we know equilibrium constants for. What I want to know now is determine the equilibrium constant for xenon difluoride plus fluorine gives you xenon tetrafluoride. So related chemistry, xenon and fluorine chemistry going on here, but I want the equilibrium constant for just this reaction. So let's see how that goes.
All right, so we want the equilibrium constant for xenon difluoride plus fluorine gives me xenon tetrafluoride. So I'm going from between these two compounds, I'm adding in basically some extra fluorine. And we know it's going to be based off these two reference reactions, right? We have these other reactions involving a lot of the same things. Xenon and fluorine are the only atoms here. Similarly, we've got xenon and fluorine. So the question basically becomes like, how do these steps combine to give you this overall reaction? So we can think about these as kind of small steps, like we've seen, like the idea of like a mechanism. What is kind of the overall process that these could combine into? So this overall reaction is the idea of xenon difluoride plus a fluorine, giving me xenon tetrafluoride. And that's what we're kind of imagining is going on, kind of a one-step process. Here I have the reaction of xenon plus fluorine, make xenon difluoride. xenon plus 2 fluorines to make xenon tetrafluoride. So how can I think about these as kind of intermediate processes? One of the things is I know I need to start with xenon difluoride. So one of the things you want to kind of key in on in order to figure out this process is what sort of compound shows up in this kind of target equation that's only in one of my references. So like xenon and fluorine, the elements show up in both of these. They're just going to kind of probably cancel out is what that means. Xenon as an element doesn't even show up anywhere. So that's not going to be useful. But the xenon fluoride, difluoride that we have right here, this needs to be a reactant. Right? So what that means is we need to envision, what we kind of imagine is like, right, I have the overall process I'd be looking at is instead of forming xenon, it's going to be like, all right, what I'm going to do is I'm going to take xenon and break it apart. I'm going to take, right there, yep, get the pen to work. I'm going to take my xenon difluoride solid. What I'm going to do is I'm going to react that, and it's going to go in the opposite direction. I'm going to get xenon and some fluorine. Now what I'm going to do, okay, well now the xenon and the fluorine, if it had one extra fluorine or two fluorines, that could make xenon difluoride. Sorry, tetrafluoride. So what I could think about doing is I could take these and I could think about them as steps. I start with the xenon difluoride. The first step is I take that and I break it apart into just xenon and fluorine. Then I take the xenon and some more fluorine and I combine those into xenon tetrafluoride. Right? This would be something along the lines of like forming intermediates, and those intermediates react to make your product, or say some more intermediates with some more reactant to make your product. So we've seen this kind of idea before. You can kind of take these reference reactions and think about how they can be rearranged and combined to give us what we want. We do want to be sure that we add those kind of all together, that it does give us, you know, what we expect. The xenons cancel. That shouldn't be a 4. That's a mistake. Sorry, that was a typo. I was doing 2 times 2 in my head. We want to cancel it out. The xenons cancel. This fluorine and that janky 2, the coefficient cancels. And so what we can do is we can see, okay, well, what would be left? XeFe2 solid, XeF2 solid plus that F2 would be in equilibrium with XeF4 solid. So because we have added these reactions together, the equilibrium constant of this is just going to be the product of these two. This is a reference reaction we've used. So this we know that's Kc2, and that's going to be equal to 782. This right here is the reverse reaction of this top one. We can call this like Kc prime or whatever. It's just, you know, a new one. 1 over 124 because it's the reverse direction. So this forward direction is slightly product favored. This reverse reaction needs to be slightly reactant favored. Where's that? 8.1 times 10 to the negative third. So what that means is the equilibrium constant for this overall reaction is going to be that Kc prime times Kc2. Be equal to 8.1 times 10 to the negative third times 782, which is equal to 6.31. And so this is functionally useful. It's not too crazy hard to find equilibrium constants for reactions that look like this, elements forming compounds. And so then you could, use that to predict equilibrium constant for this process. If I have XeF2 and I expose it to F2, will some XeF4 form? Yes, some will. Will a ton form? Probably not. This is product favored, but not by very far. But it does mean this really is an equilibrium. Another thing that it implies is that if you have XeF4, this equilibrium constant isn't crazy high. If you have just XeF4, some of it is going to just fall apart and become XeF2. We can use some fluorine. So really, any of these that you have present is really going to be in a reaction, or in equilibrium. Another nice thing about coming up with this value in this way is we can really understand it in terms of this step process. So XeF2 doesn't really want to fall apart, right? This equilibrium constant now becomes reactant favored. XeF2 is kind of stable, right? That Kc is negative, it's less than 1. So this really doesn't want to fall apart. This does want to happen, the Kc2, but it just wants to happen a little bit more, right? And it's also confirmed in the value of these Kc's that we can see up here by looking at this reference information. The reason why it is favored, this equilibrium constant down here, is greater than 1. The reason why is that XeF4, this equilibrium constant is bigger, right? 700 versus 100. So this is more product is formed here, meaning XeF4 is more stable. Whereas XeF2, yeah, it will form, but not a ton. And that's indicative of this idea that, this is more stable. This is stable relative to the elements, but not that stable. This is just a little bit more. That's why this equilibrium is product favored, not by a ton. If this was like 10,000 and this was 100, this equilibrium would be really big. And conversely, if this number was bigger, because you divided by it, the resulting product would also be smaller. So you kind of understand this number comes from the relative values of those two.
Participation 213, question 3. Determine the value of Kc for each of the reactions below based on the following reference information, and characterize each reaction as reactant favored or product favored. So the reference information I have is this reaction 2 SO2 gas and O2 gas yields 2 SO3 gas, and Kc for that is 67.2. So then the two reactions I want to know, the value of Kc and whether or not it's reactant favored or product favored, are these A and B. 2 SO3 gas becomes 2 SO2 gas and O2, and then 4 SO3 gas becomes 4 SO2 gas plus 2 O2 gas. This is the third question on participation 213, due Friday, February 13th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where there are the links to these videos. Again, determine the value of Kc for each of the reactions below these reactions based on this reference data. I also want you to characterize each reaction as reactant favored or product favored. Okay, 3 questions on participation 213. You want to find all 3 of those questions, get them answered, get those answers submitted over on Blackboard by Friday evening. This weekend, you just got the week 5 homework. No post lab because we did the test. You do have that lab group evaluation. Just as a reminder, for week 6 on those labs, you're going to be in a new lab group. You can just look in the lab notebook to see what role I gave you. I assigned roles to everyone. You can rotate everyone had to be every role in the rotation. So you'll just in the following week, you'll rotate into new roles. If you have any questions about anything, let me know. Be sure to check out the Friday participation answers. Also, your test grades will be posted by Friday afternoon, and then I will pass your tests back next week. If you have any questions about anything, don't hesitate to reach out. Otherwise, have a good weekend. Bye-bye.